I wanted to record a quick tutorial covering a couple of extras related to the tutorial I just recorded on geometry nodes. I apologize, I've got a bit of a cold, so I'm going to sound funny, but I wanted to show you a couple of alternate ways of doing some things based on some feedback that I got. At least on this first one, we're going to talk about rotation. When we had set this up, we used distribute points on surface and then an instance to points, which are basically the core nodes in this setup. And then we determined the rotation of these large stones based on the normal of the surface that they were laying on. And we used a node setup that allowed us to capture that information. We captured an attribute, which was a normal, and then we fed that into an align to vector node. And then we used a random values to randomize the node once it had been aligned. So somebody pointed out that there was actually a somewhat more direct way of doing that. And so I learned something new. Let's go ahead and remove the rotation all the way together. And you can see now that these are no longer aligned to the surface. So let's come down to this area where we had taken all of this rotation stuff. Let's go ahead and just kind of delete that and start over. So everything has disappeared because we broke the mesh connection to the source geometry. So let's take this and put this back into mesh so that we've got our stones that are unrotated. So they pointed out that there's a rotation output socket here, and all you got to do is take this and drag it into the rotation of instances on point, and look at that, it aligned it for us. So that was nice and fast, but one of the things that we did in the tutorial was to also apply a little bit of randomization to the rotation. Let's go ahead and set that up with this approach. So the first thing that we need to do is to introduce another node that we haven't seen yet called rotate rotation. So Shift A, rotate, and then it comes down here, rotate rotation. I love that one. So let's go ahead and plug in the rotate output socket from our distribute points on surface to rotation. And then we're going to plug this in to our instances on points. So nothing is going to change because we haven't given it any values yet. But we do want to rotate around the local x-axis. So it's important to switch that over. So nothing has changed because all the values are 0 essentially. So let's come down and add a random value. So we did this on the last one. We need to make sure and set it to vector to match the current data formats that we're using. And then we're going to use the combine X, Y, and Z. And this is where we grab the rotation value that we've put in. Now I'm going to come over here to rotation and make sure it's set to 0 so we can see what happens when we add values starting from 0. So we come down and put this into Z because that's the axis that we're aligning to. Plug this into the max value. So it's going to randomize from the min values, which are 0, to the max that we're putting in. And then we take this, we move these out of the way, and then we plug this into the rotate by. Okay, so now we can come over here to our rotation values and we can begin rotating them. So it's just a little bit of a different approach that I had used in the first place. But I think what this does is it really helps to sort of illustrate that in a complex system like this, there are generally going to be multiple ways to achieve something. So I thought that was a really good suggestion that the commenter had made to me to use that, and then we just add our rotation functions to it. The next part, let me turn off these big rocks. Let's turn on the little rocks, and let's take a look at these here. So I've got all of these little rocks, and these are such that I want to have a lot of them around the perimeter of the lake. Let me switch over to a camera view so we can kind of see this more closely. So here are those little rocks, but I'd really like to have a lot more of them. However, as soon as you start getting these up, it can, you get all these instances up, it can start really degrading the performance of your viewport. So we can actually use the switch function and the isViewport node to help us with this. So let's just come over and remind ourselves how this is set up. You can see over here in the add-on, there's a density input that we put in. And when we look down at this core distribute points on faces node, there's a density input. And so we have our input value from here that's being driven in through this density group where we multiply it against one of the vertex groups that we're using as a weight map to make sure it's only being distributed basically along the shore. Okay, but that just comes back down to the density input, and it's pretty simple. So what we need to do is create a condition where we can increase the density quite substantially without having to burden the viewport with displaying them all. So what we're going to do is we're N key, come down here to the group sockets, select density, and we're going to add a second one. Let's come back to the first one. We're going to call this density rendered. And then the second one we're going to call density dot displayed. So those will now show up in our group input down here. So what we need to do is we need to multiply each of them, because they're going to be separate values, against the weight map that we're using. So currently the first one is tied into the rendered. So that comes up. Let's just rename this so we're really clear what's happening. Let's rename this to math rendered so it's really clear. And then we just need to duplicate this. So Shift and D, and we'll bring that right down below. And let's go ahead and rename this one displayed. Okay, and so the input for this one comes from the displayed variable, the density displayed variable. And then we just need to tie in the attribute, which are just floating point values that get multiplied against it so that our instances only show up here. So now we need to make it so that the switched function automatically chooses when to use either of these. So let's do Shift A, and we're going to type switch. We're going to bring up a switch node right here. And then we need to do Shift A viewport is viewport node. That's the condition. If it's a viewport, we're going to have it switch conditions. If it's not a viewport, we want to use the rendered node here, the rendered math, which will use a higher value. Oh, so I need to switch this. See, it's in geometry. We need to be in a floating point format for it to accept that. And then if it's true, meaning if the viewport is displaying the geometry, we will use the displayed node output value here. And then finally, this comes down and over to the density input of the distribute points on surface. Now you can see it's disappeared because the default value for density displayed has gone to 0. So let's go ahead and set this to 10, and then it matches what we had done previously. Let's take a look at that. And you can see those rocks, but we'd really like a whole lot more of them there. So this is where you would come over and we could put up a whole bunch of them, like 650 for being rendered. And then when we come over and do a render, you can see now that we have a whole lot more rocks. So we're not being burdened with having to display these. And frankly, it wouldn't really do us anything from an artistic standpoint to have to see these. I mean, having some rocks, we're not going to be getting the camera like down to a tree, for instance, where you definitely want to see the position of trees as you have them specified via a density function. But small rocks, well, not a big deal. So this is a nice way of using that switch function to determine what the density is that you want to be. And the great thing is, in a close-up view like this, it's not going to draw all the instances that are off screen. So you can come in here and you can test here. Like I can test and see what that's like. But where the problem's going to show up is when you zoom out and you try and view this from a distance where it has to draw all of those. That's when you're going to get bogged down. Then you get much, much, much faster performance than if you came over and tried to have a whole lot more of them where it bogs down. So this is a really nice function of this is viewport combined with switched, and just having it do a different math node combined with a different input for each of those conditions. So there's another thing that I want to show you that's not geometry node related exactly. It's a shader node thing, but it's still kind of an interesting thing in case you didn't know about this. So I've got this grass geometry, and all the grass by itself is all sort of the same color, and it's a little bit boring. So there's a cool thing that you can do to give it some randomization. Each of these strands of grass are separate pieces of geometry, and we'd like to have a way for the material system to give us randomization as it shades each one of those pieces of geometry. And the way that you do that is you generate a color ramp, and I've taken the color and I've just put in these knots here that I've assigned variations of color. So I want some of the pieces of grass to be like they're dying or dead, and then I've got some of the other pieces of grass that are, more lush, more vibrant, more green, that type of thing. Well, what you do is you Shift A, type in geometry, and then this node shows up. And at the very bottom, there is this random per island, where island refers to a piece of geometry that's unconnected to other geometry, but it's in the same mesh object. And when you do that, that's the factor. And we're going to drive this in. Let me pause over here. We're going to drive that into the translucent BSDF and also into the principled BSDF that I'm mixing together with the mix shader. Okay. And then when we re-enable that, you'll see that it produces more randomization in the coloration of all the little bits of grass that are there. And I find that to be a little bit more interesting and less monotone for that graphic